So if you haven't discovered yet, hopefully you've started your studying, but if not, if you go to, come on. All right, if you go to exam prep and homework solutions, so the review outline, everything on the exam is highlighted on that review outline and things that we emphasized in class. There's nothing on the exam that wasn't stuff that we emphasized in class and is on that review outline. Okay, some extra practice problems from the book. More physics problems from the book. And then there's even more practice problems from an online 271 that I don't really have any association with, but there may be, so whatever's in that list that's related to what we did. Don't go looking, don't work on problems that are not related to stuff we emphasize, okay? And then again, one handwritten page of notes you can bring. Other questions? It's the same format. It's going to be part multiple choice, part free response.
No calculator period, or just no graph?
I will let you know. But yeah, so I will let you know tomorrow. I got to see what we do on this one. I don't remember. Other questions about the exam on Friday? Okay, so let's look at some of the. Let me just quickly talk about. I'll do that later. So let's talk about. Oh, and then for the hydrostatic. It's not. What happened? No, that's not it. Let's be here. For this last web work, I extended the deadline to tomorrow at 5 p.m. and gave you everyone 3 more attempts. Okay? But if you're catching on to what we've done in the last month, just the setup, the setup of these hydrostatic force problems, like the small example I did at the end of class, introducing you to the formulas and the basic approach, combined with all these other examples we've done of work, volume, all these things should have been sufficient groundwork to do these. Once you know the basic formulas for hydrostatic pressure, and you see a very basic example, then you're just applying all the stuff we've learned in the last month to this kind of new scenario. Okay? So it was absolutely fair for me to have it due at 9, but I'll extend it till 5 o'clock tomorrow and give you 3 more attempts on those. Okay, and let's do a couple of them, okay? So this one. So for this one, we've got this plate, and because it's trapezoidal, meaning these edges are linear, the width, so we're going to, just like we talked about, we're going to take a typical strip. We need an element for which we can calculate the force. And so because pressure varies with depth, we need an element that's at all the same depth, right? Because pressure varies with depth, the element for which we'll calculate pressure has got to be all at the same depth. So that's a horizontal strip. Okay, so so we know that pressure equals density times depth. Wow, something landed in my throat. I hope it's not alive. All right, force equals pressure times area. All right, so for the pressure, we've got mass density. Remember, we need weight density, so it's going to be 975 times the 9.8. That's our rho, that's our weight density of the fluid, times the depth. Okay, so the depth is going to depend on our frame of reference. So here's the deal. We're going to set a frame of reference, and then everything we do has to be in terms of that frame of reference. Common mistake students make is when they do one part of the problem, they're assuming one frame of reference. And they do another part of the problem, and they've automatically they're in another frame of reference. So we have to set up the frame of reference, and then every expression that we set up has to be according to that frame of reference. So a couple possible choices would be the top of the plate as x equals 0, or the surface of the water. Either is fine. So let's do the surface of the water. That's fine. But once we choose that, so here's our x coming down like this, and then x equals 0 is up here at the surface. Now, once we choose that x, everything we do now has to be according to that frame of reference. So, what's the depth of our typical strip in terms of the x that we picked? It's just x, okay? So that's going to be the easy part. All right, so we got our rho, or our pressure. And so the little bit of force is going to be the pressure times a little bit of area. And so the little bit of force is going to be, it's the pressure. We just found the pressure at 9.75, 975. It's 9.8. X, okay, times a little bit of area. And so our strip is a rectangle, so it's going to be width, W, times, what's the other dimension? Delta x. So now what about the width here? Well, the width varies with x, so it's going to be, we have to have a relationship, either a function, or we're going to have to set up a linear function. So does it relate linearly to x? Does the width relate linearly to x? Yes, it does. So then what we need is, we just need ordered pairs. So it doesn't matter if this side is like way more shallow and this is a real steep line, because we're not finding the equations of these lines, we're just getting the width of our strip as a function of x. So as long as that's linear, all we need is two ordered pairs and we can write our equation of the line. All right? So kind of like the inclination or the steepness of these sides doesn't matter. As long as they're straight, the width is going to vary linearly with x. Okay, so we need some ordered pairs here, x and w. What do we got? When x is 3, w is? Yeah, so when x were 3 foot down, the width is 4. And then the width is 7 when x is 5, right? And so there we go. We're starting. So now you got any way you can build your relationship. It's going to be a line where it gives you the width w for any x. This is a function, right? This is why we need functions, because w changes with x, and we need an expression for w for any x, right? So the rate of change would be change in w over change in width, which would be 3/2. And then we could do w final equals w initial plus the change in w, which would be w initial. Pick either one, so it doesn't matter. So pick this as initial. Any point we can call the initial. So it'd be 4 plus. And how do we get the change in width? Well, it's going to be our rate of change times the change in x minus 3. If you have a different way of getting w in terms of x, go for it, right? So it's just given 2 points. You need somehow something from your algebra past of getting the equation of a line in terms of having 2 points. This was consistent with what we did in Calc 1. Initial plus the change, and the change by the rate of change times the change in x. Okay, so we're ready to put that in, and we've got our delta F. Question?
Okay, why is it -3 and not -2?
Because the point is 3, 4, right? So this is W initial is 4, X initial is 3. Right?
Okay.
Right, I'm using this ordered pair, so it's the 3, 4. Yeah, sure. So delta F equals 975 times 9.8 X times the W, 4 plus 3 halves, X minus 3 times delta X. Okay, so notice the depth was based on this frame of reference we picked. The width formula was based on this frame of reference that we picked. And now we get one more thing that's going to depend on that frame of reference, and that's the bounds of integration. So the total force on the plate is going to be integral from what to what in terms of this X. So you want, yeah, first strip is going to be at X equals 3. The last one's going to be at X equals 5. And then it's going to be that thing with a dx. So if we chose the frame of reference to be at the top of the plate, then what would have changed? Everything, right? So what would the depth be now? What would our new depth be? Okay, X minus 3 or X plus 3? X plus 3 would be the new depth. What would be the new function of X? Well, our ordered pairs would be what? 0, 4 and 2, 7. And whatever we get from that, right? It'd be 0, 4 and 2, 7. Finally, the bounds would be from 0 to 2. Okay? So you have to be deliberate about picking a frame of reference, and then everything you do is in terms of that frame of reference. If you're not sure what your frame of reference is, you're bound to do one thing one way, another thing another way, and you won't get the right result. Okay, questions on this example? Does this make sense? Okay, so let's look at one more of these, and then we'll do one last good example to get you ready for the exam. Last chance, questions? So this one? Okay, so we got this dam. This is the dam problem. Okay, and so we've got water. So again, we know that pressure equals rho times depth. Force equals pressure times area. Hydrostatic force. So we're trying to get all the force on this face right here on the little gate. Okay, so frame of reference. We've got some choices here. We could choose the frame of reference to be, here's choice number 1. And now I'm gonna make vertical y, because we've got a circle. We're gonna have the equation of a circle. We're gonna have x and y, so we'll keep y vertical and x horizontal. All right, so there's one possibility. Another possibility would be the top of the gate, and maybe do something like this, or sorry, like this. But I think this is the least desirable because it doesn't help with the circle and it doesn't help with the depth. So this is helpful because the depth is just y, right? So that makes that easy. Here, and what's more difficult about that? The equation of this circle. Now this frame of reference, if you put like the origin here, well now neither the depth nor the equation of the circle is straightforward. So maybe that's the last choice. Then the next thing we could do is to do this one. Put the center of the we could put the center of our frame of reference at the center of the circle. And what does that do? Well, we have to figure out what the depth is. That might take a little work, but this makes the equation of our circle the easiest. So let's choose this one. Just because we have to choose something, we'll choose this one. All right, so we got that a little bit, or the pressure. So, and again, we're going to have a typical strip. Right there. And so, what are we going to do? We're going to do a little bit of force is going to be the pressure, which is rho times d, pressure times area, a little bit of area. So in the end, it's going to be this. Okay, rho is easy. That's the 9,800, right? 1,000 times 9.8. Okay, so what is d? Okay, so d is the distance from our strip up to the surface. That's d. So how would we write that distance d? It needs to be in terms of what? Y, right? Suggestion.
Would it be 10 minus y?
He wants 10 minus y. Like it, or to suggest something else? Okay, so first of all, where's the 10 coming from? Where do you see 10?
Well, because the whole thing is 12 meters, but you take off 2 meters because you start at the wall.
Okay, yeah, so really, this 2 meters doesn't really have anything to do with the problem. Do you see that? It's just air, right? So we're talking about pressure due to the water, so this is just how much air there is above. That's really nothing. So really what we care about is that the depth of the water here to the bottom of the dam is 10. So that's the important thing right there. It's 10. From here to there. So if this whole thing is, so he's saying 10 minus y, is that right? So it's this 10, what is y? Y is from here to here. So what do you think about 10 minus y? The whole distance 10, take away y, gives d. Yeah, he got it. That's it. So, again, so that was a little harder to figure out. We didn't just have to write down that the depth was y. We had to figure that out. But we're going to gain some benefit back when we get to the equation of the circle, which will be easy because we put it at the center of the circle. See that? All right, so 9,800 times 10 minus y. So now we got the area. Area for is always the rectangle, so it's going to be. So what is the width of this strip now? According to our, so if we're going to have the equation of the circle is what? It's nice and easy now. Equation is x squared plus y squared equals 2 squared, right? So that 4 is not the diameter, but it's the radius squared, right? 2 squared. It's not the same as this 4 right here. Okay, so according to that equation of that circle, what would we say is the width of our typical strip? Don't jump the gun. So is it a x, a y, a change in x, or a change in y? Okay, so it's a change in x, but a change in x with symmetry, right? So we can just say it's just 2x, right? So we could do x1 or x2 minus x1 as a change in x, but by symmetry, this is x right here. It's the x coordinate at this point, so 2x. So it's going to be the width 2x times delta y. And now because we're doing delta, because we got it in terms of y, we write x in terms of y, and that's just from the equation of our circle. X is 4 minus square root of 4 minus y squared. Is that right? Questions on that? Last thing is the bounds, right? So now we got our tip. This is our typical amount of pressure. Sorry, typical force on that strip, right? That's the amount of force on that strip. And so we're going to add them all up. Sum up all of these forces, one of which is 9,800, 10 minus y, times 2, square root of 4 minus y squared, dy. Okay, y from what to what?
0 to 2.
0 to 2, right? The first y would be here, 0 to 2. Okay, other frame of reference we could have done was to put the origin here and say y like this, and then x like this. Here's an alternative, that's an alternative, so we'll call that y1, x1 as an alternative frame of reference. What would change if we did that? Almost everything, right? So the depth now would be what for this frame of reference? Yeah, just y1, right? What would the width be? It would still be 2x, but our equation of our circle would be different. Now notice here, now I'm making y go down. So these are all positive y's down here. So the equation of the circle would be x squared, x1 squared, plus y minus 10, right? The center is at 0, 10. This is positive 10, so 0, 10, y1 equals 2 squared. So there's a new equation of our circle for this frame of reference. And finally, the bounds would be from what to what? 8 to 10, right? 8 to 10. Or 10 to 8, whatever makes it positive, okay? So sometimes there's some weird sign things going on. So if you set everything up right and you get, everything is correct and you get a negative answer, then it's just something with the orientation. And it's just if you flip the bounds, you get the positive version. But that's only if everything else is correct, okay? So the bounds would either be 8 to 10 or 10 to 8. So occasionally that happens where you do everything right, you just have an orientation flip and you get the negative value, but force is going to be a positive quantity. Okay, questions on our setup or the other frame of reference? Yeah, please. So this one, let's see. Yeah, so to do this, so you're going to end up with two integrals, right? Basically, you have to distribute. So when you do the minus y version times that, what's our technique for that? Y times square root of 4 minus y squared. Do we need the table? I'm doing the chain rule, right? So y is essentially the derivative of y squared. So that's the easy one, right? That's the easy one. Just raise power on the composite function, right? So it'd be 4 minus, the attempt would be 4 minus y squared to the 3/2. You've got the y to cover your y squared. Okay? The other one would be the 10 times that thing. And everything else times that thing. So that's it. That's of the form square root of a squared minus x squared. That's table. Yeah, so you have basically two integrals to do. One is undoing the chain rule. The other is table. Yeah?
If there are table integrals on the test, will those be given to us?
Yes, that's the whole point. You don't memorize the table because you're using the table, right? That's the whole point of table integrals. Yeah. So either I would just tell you to set it up, or I'd have to provide you with the formula. Yeah. Yes, ma'am.
For the amounts, why do you not add like the 10 like the pressure, like the 10 meters of water on it? Like those are to calculate like the.
But the bounds are y values, right? They're the y values. Are you talking about the original setup here?
Yeah.
Okay, so the bounds are not pressure values, they're y values of these strips that we chose. So now, I've got this is the pressure. It takes into account the depth, right? Here's the depth, right here. So this is the pressure on a typical strip. So this says sum up those pressures for all the strips. And so we need the y values of all the strips.
Okay.
So the pressure, all the water on top, that's built into, so when we calculated the force on one strip, there's the depth and the pressure is in that.
So the 10 minus y is like the pressure on each strip.
No, that's the depth, right? So pressure is rho times depth. Weight density times depth. There's your pressure. So that would be all of this part right here. There, would I put a cloud around here? That's your pressure. And then force is the pressure times the area. So all of this that I'm putting a box around is the area. So that whole thing then is the force on one strip at this depth. And then the bounds of integration are the y values for each strip. So I'm going to go my first strip is going to be at 0, x, y equals 0. And so when y equals 0, look, the depth is what? 10. So it's going to, when y equals 0, this is going to be the force on the strip whose depth is 10, meaning there's 10 feet of water on it. You see? And then all those y values up to 2, what depth is that at?
10 minus 8.
Is 8. So it's calculating the force for the pressure calculated for a depth of 8 meters. So the bounds are y values, and the pressure and the force are in our typical strip that we calculated.
Okay.
Is it better?
In the previous example, it looked like you added like the depth in, but you still like the bounds included the depth.
It's all about the frame of reference. So the pressure, you just got to think, we're finding the force on a typical strip. And then the bounds are going to be, according to our frame of reference, where are the strips according to the frame of reference? So if you look back at the example, that should be totally consistent. Yeah, so those bounds are y values. According to the frame of reference, that's the key. Where did we put the frame of reference? On the previous example, we put the frame of reference up here like this, so that the x values were depth. But now we're putting the frame of reference down here. So y values are not depth. Y values are coming up from the bottom. So then that's why the depth was 10 minus y. But then our bounds have to be in terms of that frame of reference that we picked. You see?
Yeah.
Okay. Any other questions? Okay, so let's work on another example here. Yeah. There we go. I can do a better picture than that. All right, so we got an oil tanker, has a cylindrical shape with a diameter of 12 feet and a length of 74 feet, and is filled 3/4 of the height with gasoline, which has a density of 44.9 pounds per foot cube. We want to find the total force of the gas on the circular side of the tank, like the very back of the tank, and how much work would be required to remove all the gas from the valve at the top of the tanker. Okay? And if we have time, hopefully we can maybe set this up with 2 different frames of reference. That's really helpful in understanding these problems, is if you can do it in more than one frame of reference, you really got a handle on it. So that's what we want to practice that. So I'll make a sketch here, and you guys can get going. Okay, with this frame of reference, did you get what the depth is? He said 3 minus y. Agree with that? You should have found this distance from the halfway point up to the surface of the gas. That's a quarter of the diameter. So that's 3. It's 3 feet from r y equals 0 up to the top level of the gas. 1/4 of the diameter. Do you see that? So now the depth, this is y up this way, right? Y is this dimension here. And that whole thing is 3. So the depth of the slice is 3 minus y. That's the hard part about this, doing that frame of reference. Does it make sense? So quickly here, so we got the force on the typical strip is going to be, we already have weight density, 44.9, times the depth, that's our pressure, right? There's pressure, times area, which will be 2x change in y, right? 2x times delta y, where x is
36 minus y squared.
square root of, so the equation of the circle, x squared plus y squared equals 6 squared. So 36 minus y squared. There's the force on the typical strip that I drew, with the frame of reference at the center of the tank, the circle. Yeah, question?
Isn't the radius this? Wait, sorry.
You good? Yeah, the radius is 6, so it'll be radius squared. Questions on that? Okay, same frame of reference. Now the work. What kind of typical element are we lifting out of this tanker? What's the shape of it? Oh, bounce, right. Bounce for this would be? So, yeah, so the first strip is down here. What's the y value? -6. Last strip is at +3. Okay, the work. Work. Work is force times distance. So a little bit of work. I'll do blue. Red. Now this force, so this force is what? It's the weight of a typical element that we got to move out of here. What is the shape of that typical element that we're going to move out of there?
Square.
A rectangle. It's like a wafer, right? Like a rectangular wafer of gas. That's what we have to move out of this thing, right? If you took a slice, all that whole slice, that horizontal slice, has to go the same distance, right? And now the distance is not the depth. What is the distance? So now what's the this distance is what? For the work is from here to here. We got to get it out the top of the tanker, not to the top of the surface. So it's the same idea here, but now it's going to be 6 minus y, not 3 minus y, right? Because it's going to be the whole radius, 6 minus the y coordinate. Here's the y coordinate of the slice. The whole radius is 6. So the distance that thing has to go, that we have to move it, is 6 minus y now. So the force is its weight. What's the weight? Weight density times volume. Length times width times height. We just said the distance was 6 minus y. Length times width times height is of the typical slice. What's the length of it? 74. The width is 2x. And 2x is, this is x over here, 36 minus y squared, square root. There's our width, 2x. The height of it is tangent y times 6 minus y now. Bounds are from? Same, right, it's the same layers, but now the layers are three-dimensional layers rather than two-dimensional strips, but it's the same, negative 6 to 3. So another good frame of reference would be y equals 0 on the top of the surface of the gas. That would make depth easy because it would just be y. But then your circle is offset. The center's not at the origin anymore.